Hello viewers, welcome to my channel JEE Olympiads and AP Physics with Ambarish. And today I have brought another topic that's given in NCERT, but somehow students remain confused about this. The topic is about relationship between magnetic intensity, magnetization, susceptibility, and how to use Ampere's law in magnetic materials. So students find this a bit uncomfortable, and that's why I've decided to do this video today, and I'll be presenting a problem to motivate the discussion so that you understand that you need more theory to do the problems. So the problem that I've selected is, this is an Aerodo problem 3.275. So let me read out the problem and then I'll derive the relevant theory and then we'll do this problem. Okay, so let's see. A direct current I flows in a long, round, uniform cylindrical wire made of paramagnetic with susceptibility chi. So this is some wire, and in this there is some current flowing like this, and let's say I is that current, and the susceptibility of this is chi. So chi is the susceptibility. Okay. So what do we have to find out? We have to find out the surface molecular currents I dash S. Okay. So what do we mean by surface molecular currents and volume molecular currents? You see, if I have let us say a cylindrical section and we have local molecular currents induced, you know that because of the magnetic field induced by the flowing current, there will be some molecular currents flowing inside this, and these molecular currents may be either they can be volume currents, and as well as there can be some surface currents. So for example, if I have a section like this and in each of these circular sections some current is flowing, it will be equivalent to a surface current. So that depends on kind of magnetization that happens in the material. There will be some surface molecular currents and there will be some volume molecular currents. Okay. So what do we have to find out? We have to find out the surface molecular current total flowing on this surface because of magnetization. Surface molecular current is the current due to magnetization, apart from the current that is flowing that we have flown using a battery. So there are some additional currents that we need to find out. Okay, so they may be like this. If you see in the top view, there may be some currents flowing like this. We don't know, but there will be some surface currents. Okay, and volume molecular currents. And how are these currents directed towards each other? So this is the question, and I believe for most of the students NCERT theory will appear highly insufficient to do this problem, although it turns out that if you do a little more derivations based on whatever is already presented in NCERT, you can do this problem. So what I'll be doing, I'll be using the results presented in NCERT and I'll be extending them a little more to make it easier for solving the problem. So let's see. So what results I am going to prove based on NCERT results. Of course, we can do this theory in lot more detail. It's given in Savelev's book, but I think that will be overkill. So I have assumed the NCERT results as it is without proof, and based on that I am going to develop further. Okay, so what results I am going to prove based on the accepting the NCERT results as they are. First is integral of H dot dl is I free enclosed. So here H is magnetic intensity that is defined in NCERT, and I am also going to define in this document shortly. And then the other thing I will prove is that integral of supposed to be contour integral, so of magnetization dot vector dot dl is bound current, total bound current. Now what do I mean by bound current? Bound current is the same thing as a molecular current. Okay, so when you apply the external field, the materials, they create their own currents, they arrange their magnetic dipoles in such a way that molecular level currents are generated. So those things we are calling as bound currents. So if you want an analogy with the electrostatics and dielectrics, so this is somewhat like analogous to free charge and the bound charge, and bound surface charge and the bound volume charge. So charge occurring due to polarization of the material. Okay, so these two results I am going to prove based on whatever is given in NCERT. H is the magnetic intensity and M is the magnetization, which is nothing but magnetic moment per unit volume. Okay, So now in any material, the net field is due to following reasons. One is the applied external magnetic field, and this external magnetic field is due to currents created using batteries. So there might be some copper wire or metallic wire through which I am passing current. So that is my free current, okay, that I am creating using batteries, okay. And then the other component of field is due to the magnetization of the material. So in response to the external applied field, the magnetic dipoles will orient themselves to create their own field, and that I am calling as Bm vector. So B naught vector is the applied field and Bm vector is the field that has come in the response of the applied field, okay. So now what will be the net field? So net field is B vector is nothing but B naught vector plus B due to magnetization, right? Now it turns out that the field due to the magnetization of the material is directly proportional to the magnetization of the material, degree of the magnetization. So if there is greater magnetization, that is greater dipole moment, magnetic moment per unit volume, then there is greater Bm. And the relationship is given in NCERT as that B due to magnetization is mu naught times magnetization vector. So this I have not proved, I have stated as a fact as it is from NCERT, although it's proved in Savelyev, okay. So I'll just take it as it is. If you want, you can refer to Savelyev for greater details, but as I told you, it will be an overkill for JEE purposes. So for JEE purposes, you can stick to whatever I am presenting in this video, okay. Now we define two types of currents, as I said: free currents created by passing current through wires, and bound currents created due to magnetization of materials, also known as molecular currents, okay. So now using Ampere's law, what we can say is integral B dot dl is equal to mu naught I enclosed, right? So what is integral B dot dl? So you know that total B is composed of B naught and Bm. So integral B dot dl is nothing but integral of B naught dot dl plus integral of Bm dot dl. So B naught is due to the free currents, okay. So individually I can say that integral of B naught dot dl must be equal to mu naught times free current, right? This is the usual Ampere's law. Imagine that there is no magnetization, so there is no bound current and there is no B due to magnetization, then of course B naught dot dl integral will be nothing but mu naught times the current flowing through the different wires, okay, actual current that is created by batteries, right? So integral of B naught dot dl is mu naught times I free, and then of course total current is I free plus I bound, so total B dot dl must be equal to mu naught times I free plus I bound or I molecular, right? And so integral B naught dot dl is mu naught times I free. Now I can subtract equation 4 from equation 3 and I get B due to magnetization dot dl is nothing but mu naught times I bound, that is molecular currents. Just subtracted equation 4 from equation 3. So I can say now using equation 2, where is the equation 2? Here. So Bm is mu naught times m. So I can say that mu naught times m dot dl is mu naught times I bound, or I can say integral of m dot dl is simply I bound, okay, that is molecular current, right? So this is one relation that I wanted to prove, that magnetization integration over any contour is equal to the bound current passing through the contour, right? Now we are going to define a physical quantity H, which is known as magnetic intensity, which NCERT has defined. That this is the basic definition of H vector. So H vector is nothing but B vector upon mu naught, that is the total field in the material divided by mu naught minus the magnetization. So this is your H vector. So it turns out that this is written in a very complicated format, but actually H vector is something very simple that I am going to prove shortly. So if I go by this definition itself, you will find that this is equivalent to something very trivial. So what is that? So H is B by mu naught minus m. So I can say that B vector is mu naught times H vector plus m vector, right? Okay. So now H vector so this B vector is what? So B vector is B naught plus B due to magnetization. So I take mu naught here and I write B as summation of B naught plus B magnetization upon mu naught, and then I take this m here. So H vector is nothing but B naught plus B due to magnetization upon mu naught minus this m vector, right? Just rearrange the equation 8 prime. So this becomes B naught by mu naught plus Bm upon mu naught minus m vector, right? But you know that from equation, if you see equation 2, Bm by mu naught is nothing but m vector using equation 2. See equation 2, this Bm is mu naught times m, right? So that's what I've written. So Bm is mu naught times m, so I can say that Bm upon mu naught is m. So this cancels off, so this is also m and this is also m, so this goes to 0. So actually H vector is nothing but it is simply B naught upon mu naught. Okay, so that would have been a simpler way of defining H vector, but it's fine. So this is what's given in NCERT, and this is what I have proved, that this is also equivalent to this. So in a way you can say that magnetic intensity is just another measure of applied magnetic field B naught, just that it is scaled down by a factor of mu naught, that's all. Okay, so magnetic intensity, its units will be different because mu naught is not unitless, but it's just proportional to the applied field, that is the field created due to the free currents. Okay, so this is one. Okay, so now, so integral B dot dl, so I can, based on this, what I can write is integral of mu naught into H dot dl. See, integral B naught dot dl is mu naught times I free, that's what I have written. See, integral B naught dot dl was mu naught times I free, and B naught can be written as what? So B naught can be written as mu naught times H, so that's what I have written. This is integral B naught dot dl, or integral of mu naught H dot dl is equal to mu naught times free current, right? Okay, so mu naught you can cancel off on both sides, and you are left with integral of H dot dl is equal to I free enclosed, right? So this is the other result that I wanted to prove. So one was integral M dot dl is equal to bound current enclosed, and the other result is integral of H dot dl is free current enclosed in the loops, right? Also, magnetization is directly proportional to the H vector. So this is also given as a fact in NCERT, that more is the applied field, more is the magnetization of the material, which also seems logical, because when you apply more magnetic field, more dipoles will align, and in a linear magnetic, so magnetization will be directly proportional to the applied field or applied magnetic intensity. Okay, so that means what I can write then, B vector was what? B vector was B naught and plus B due to magnetization, right? So B naught is nothing but mu naught times H, right? And B magnetization was mu naught times M, right? But M itself is chi times H. So if you can express M in terms of H, so you can just write total B vector is nothing but mu naught times H into 1 plus chi. Mu naught H is just B naught part, and mu naught times chi H is nothing but B due to magnetization, because chi H was M and mu naught times M is the B due to magnetization, right? Now 1 plus chi, this number is known as the, chi itself is known as susceptibility, and 1 plus chi is known as relative permeability, right? So instead of 1 plus chi, I can put mu relative, and mu naught into mu relative is known as the permeability of the material. So I can say that B total magnetic field is nothing but mu times H, right? Magnetic intensity. So B vector net field is equal to permeability times the magnetic intensity, which is the measure of applied field due to the free currents, right? So now I can say that then B upon mu, so B upon mu becomes nothing but H, and integral H dot dl is free current enclosed. So that gives me integral of B by mu dot dl is equal to free current enclosed, right? So this you can consider as Ampere's law for magnetics, and this is analogous to the Gauss law for dielectrics, where you were writing integral of K times E dot ds is equal to Q enclosed by epsilon naught. That's what you were written. Q free, sorry. So you were writing integral of K times E dot ds was Q free upon epsilon naught, right? So it's something similar. Okay, so instead of integral B dot dl is equal to net current enclosed, we can talk in terms of only the free currents enclosed and ignoring the molecular current. So sometimes it's handy to use this formula, right? Now let us come to the current problem. So what is the current problem? Here is the current problem. So direct current I was flowing in this wire, and it has susceptibility given as chi, and we have to find the surface molecular currents flowing on the surface, whatever the direction, I am not worried about, but just there will be some surface current. So total surface current I want to find out, and the volume molecular currents at the molecular level, what is the currents due to the magnetization. Okay, and how are these currents directed towards each other? That's what I have to comment on, right? So let's see. Okay. So let's say volume molecular current enclosed up to a radius small r is given by I prime small v, right? So we know that integral m dot dl is nothing but total bound current, and integral, so just rearranging this, I can say that integral of chi times h dot dl is I bound. So you take chi outside, so chi times h dot dl is I bound, or we can say that chi times I free enclosed is I bound. So bound current up till radius r, I can simply say that it is chi times the free current enclosed, right? So for the shown loop, for this loop, if I just consider this white colored loop, so what is the free current enclosed? So free current enclosed is total current is I and total radius is capital R. So the current per unit area is I upon pi capital R square. Okay, let's say total radius is capital R. So up till small r, the current enclosed is this into pi into small r square. So that's what I've done. So I by pi capital R square into pi into small r square, and this chi comes as it is, and this should be equal to the volume bound current up till radius small r. So that gives me this as the volume bound current up till radius small r. But the question asks us to find the total volume bound current. So just puts capital R for small r also, and then we have total volume bound current is simply chi times the free current, right? So I prime V is equal to chi times I. So this was one answer. Volume bound current, that was asked in part B of the problem. Now we also need to find out the surface molecular current or surface bound current. So once again, I can consider an Amperean loop outside the conductor, completely outside the conductor, and I can now say integral m dot dl is I bound enclosed. But you see, this loop is entirely in free space, right? So I could have drawn it somewhere here also. So the loop is entirely in free space, so magnetization on the loop is 0. So that means what? Net bound current enclosed is 0. So what is the total bound current enclosed? That is the surface molecular current enclosed plus the volume molecular current enclosed. So that's what I've done. So we know that since the entire loop is in free space, m at every point of loop is 0. So we can say that 0 is equal to volume bound current plus surface bound current. Or I can say that surface bound current is just negative of the volume bound current. So surface current is minus chi times I. So negative sign implies that the surface currents are exactly oppositely directed to the volume bound currents. Okay, so that's what I've written. Surface molecular current is opposite to the volume molecular current. So just to summarize, in general, you see, in the magnetic materials, the total magnetic field may be complicated, but free currents are generally easier to handle. So that's why it's easier to work with H vector rather than working with the total magnetic field vector, because suppose susceptibility itself is variable, then things will get really complicated. Although if a uniform current is flowing through the wire, the free current is uniform, we can easily calculate the H vector, okay, just by the normal integral H dot dl is I free, because H only depends on free currents and we don't need to worry anyhow complicated currents are moving inside. So once we know the value of H vector, then we easily can find out the magnetization, local magnetization using chi times H. And once I have magnetization, local magnetization, then I can find the field due to magnetization as B magnetization is mu naught times local magnetization vector, right? So depending on different susceptibilities at different points, we can find the magnetization at different points in the material. And then we can find field due to magnetization, and total field can be found by just superposing the applied field with the field due to magnetization. So that's how the H vector makes our life simple. So I hope you understood this discussion, and I highly recommend that you once again see this video so that the concepts stay with you, and preferably you should also make all these derivations with your own hand, because otherwise I believe that this is fairly volatile stuff, and it's kind of new for most of you. So that's why I decided to present it, because from JEE 23 this is going to be included in advanced, and I'm expecting that there will be fairly complicated problems on this concept, and I expect that students would be solving Erudov problems on this topic as well from the next year, and that was the motive behind doing this video. I hope you found this video useful. If you did find this video useful, please do give it a thumbs up, and please share this video as much as possible with your friends through WhatsApp, Telegram, Discord, or whatever medium you use for networking with them. And most importantly, if you're not already subscribed to my channel, please do so right away. Hit that subscribe button, and please thanks a lot for watching this video, and I'll see you in the next one. And as always, God bless you all. Thank you.